much here for the invitation and introduction. It's a pleasure to be here in this protein statistics seminar and also to be in USC for the whole year. So I'm an assistant professor at Bilkent University, and now I'm on sabbatical leave. So I'm visiting USC for the whole year. Got it? Okay. So yes, it's pretty related, especially the motivation part. It's pretty related. The course will have a similar motivation. It will go through similar subjects. So this is a joint work with Jin Ma, who is about to join us. I guess he was just giving some midterm. And also Wenqian, who was a PhD student here at USC with Jin Ma. And it's on set-valued stochastic analysis. So this is our first work with Jin, and we initiated this work back in 2019, before the pandemic, when when I was visiting USC for just 2 weeks. So we worked on this during the pandemic, and finally it's now accepted for publication, and I'd like to present our findings. We still continue working on this subject. I will try to conclude with some remarks on problems that are still open, problems that we are still working on. So these are sort of the summary of our first attempts to establish some theory on set-valued stochastic analysis, which is motivated by some financial considerations, as I will explain soon. Oh, okay. So our motivation comes from finance, from risk measurement. So there is a well-established theory of risk measures in static and dynamic frameworks, and in continuous time they are connected to backward stochastic differential equations. So I would like to motivate our work by talking about this connection briefly. So let's start with the well-understood case, which is the so-called scalar case, where we are interested in measuring risks of one-dimensional or real-valued financial positions. So let's imagine a situation where we are between time 0 and time capital T, and at time capital T we have a financial position which is a real-valued random variable. So what the risk measure at an intermediate time T does is to calculate some capital requirement for each financial position. So you have a functional from the space of F capital T measurable random variables into the F little t measurable random variables, let's say in the L2 framework. Typically, we want this kind of functional to have some nice properties, such as monotonicity or cache additivity, sometimes called translativity, and also convexity, because they have certain financial interpretations. This kind of theory has been established at the beginning of 2000, around that time, and now we have a lot of results and some satisfactory theory for risk measures, dynamic risk measures. If we look at one single financial position and the evolution of its risk backward in time, this creates a stochastic process. So now I freeze my C, but I change T. So I get a stochastic process for each terminal position. And what is a desirable property for this kind of a collection, what I call a dynamic risk measure, is time consistency, or as well known in probability, the Tower property of conditional expectation. We can just set this as a property that should be satisfied by dynamic risk measures beyond beyond conditional expectation. If you like, you might call it some sort of nonlinear expectation, for instance. So this is just the tower property. You calculate the risk at an intermediate time and recalculate the risk at some prior time s. This is the same as measuring risk in one shot right at time s. So this is some desirable feature of dynamic risk measures when you consider a bunch of conditional risk measures indexed by time. And the connection between this and BSDE is sort of natural, because those properties like monotonicity, convexity, and so on, also time consistency, are naturally satisfied by solutions of BSDEs in many situations. For instance, let's look at this simple standard BSDE, where we have a driver function f with a bunch of inputs, the time, and the components of the solution. So the first component of the solution, usually denoted by y, here I call it rho s and rho t here. So that's the main part of the solution. And that's the auxiliary part, which appears in this martingale representation. So this is the BSDE whose terminal condition is my financial position, and the rho part of the solution will be my risk measure, provided that my driver is nice enough. For instance, immediate from comparison theorem for BSDEs, we have that this solution satisfies some monotonicity, which is a very natural property of risk measures. So if you have a higher C, then the risk will change monotonically. It will have lower risk. If the driver function is free of the y part, then the solution satisfies some sort of cache additivity. So I have rho t of x plus m if m is rho t measurable, t measurable. Okay. Then this will be rho t of x minus m. This is what I mean by translativity. So if the driver f is only functional, let's say e and z, but not of y, then this is satisfied, and indeed this is sort of if and only. Although the theory for yes.
Convexity.
Oh, I forgot to mention this.
F can depend on y.
Of course, if you want the risk measure, you should remove the dependence on y.
But with y, then it's not necessarily convex. With y, if f is convex, does that imply low?
You might need something in y as well.
Yeah.
Yeah. I think so. Yeah. Let's ignore this one. Time consistency is very natural because of the flow property of the solution. And indeed, these kind of properties for BSDEs, solutions of BSDEs, were quite well known to BSDE people even before risk measures were studied in 2000 and later. For instance, if you look at this 1997 paper on BSDEs, and also another paper by Tang from 97, you already see all those properties except transitivity, except this one, which was the new feature of risk measures. And later people studied transitivity and also the reverse question. For instance, when you start with a risk measure, when can you ensure that this comes from a BSDE? This kind of converse result was studied by Emanuela Rosazza Giannin, and also there is a paper of Jin and this is former PhD student Yao on the quadratic case. And in terms of the convex conjugate of F with respect to Z, one can even provide a dual representation theorem for this kind of risk measure coming from a BSD. What motivated us for this work was the multivariate extension of this framework. When you have a terminal value, which is multidimensional, how do we calculate the risk of such a financial position? So we have a vector C this time, d-dimensional vector, and there are two motivations to study such a problem. One is coming from currency markets with transaction costs. So let's say you have a financial market with a bunch of currencies, and there are transaction costs that are not negligible. Okay, so in this case, you model your portfolio in terms of different units, such as dollars, euros, yens, etc., rather than converting everything into a single numeraire. So this is one motivation to study the risk of a whole random vector. And the other motivation is on systemic risk, where you have a financial network with a bunch of institutions. And although you keep everything in the same numeraire, like US dollars, there is every entry corresponds to a different bank. So that's a different story. And it was indeed the subject of my talk in the Math Finance Colloquium last month. So this motivation might come from systemic risk or markets with transaction costs. Many nice theoretical features for this kind of situation has been already established. The important thing is that now that we have a vector, so C. So now that this is in RD, I would like to find a capital allocation which is also in RD. And I cannot really choose a minimum M for my C because we don't have a natural ordering on RD. That's why the risk of C is now defined as a set of vectors. So what is called a set-valued risk measure, or I should say L2FEO RD, three-dimensional random vectors. So if you look at R0C, this is some sort of a set with a boundary, unbounded set, and you are usually interested in calculating or characterizing the boundary of this kind of a set. So this is called a set value risk measure. The one-dimensional in the one-dimensional world, it shrinks to an interval. Let's say you have rho t of x to plus infinity. You can imagine the set value situation as an interval. If your C is one dimension. But in the multidimensional case, which is the more interesting case, there is a strict necessity to work with set-valued functions. In the one-dimensional case, you don't work with intervals, you simply stick on the left-hand side, left-hand point. Okay. The dynamic framework for set-valued risk measures is also studied by for instance, my former PhD supervisor, Birgit Rudloff, also my colleague, Zach Feinstein. We have some results which are nice from a convex analytic perspective, such as dual representations. Also from optimization perspective, we have some dynamic programming principle for optimization problems in discrete time. But in continuous time, we don't have a structure like in the one-dimensional case, univariate case, such as a BSDE or something similar, which we can use to generate set-valued risk measures in continuous time. So that was the motivation of our research, and we are still trying to understand it better. If we look at the discrete time case, what happens in the discrete time case, which is technically much easier because you simply work on a binomial tree or something similar, some random mode structure. we could characterize set value dynamic risk measures in terms of some difference inclusions and difference equations. So set valued backward stochastic difference equations, because they are in discrete time, or backward stochastic difference equations. Of course, one natural thing to do is to try to take their continuous time limits, which is something that we currently work on. But otherwise, one might also directly start from continuous time. What happens in continuous time? So you need to work on the field called set-valued stochastic analysis, which means that you need to study objects like set-valued stochastic processes, random sets. Okay, at a fixed time, you have a random set. How do we define its expectation? How do we define its conditional expectation? Can we talk about martingales in the set-valued framework? What is, for instance, conditional expectation in the set-valued framework? Is this a martingale? What are other martingales? And then you try to go slowly towards establishing a theory for a BSDE in the set-valued setting. You need some tools to study BSDEs. Okay, once you make sense of concepts like expectation and also some integrals, stochastic integrals, so you can try to also establish some tools such as ethos formula, martingale representation theorem, and so on. So these are the subject matters of set-valued stochastic analysis. And also in the set-valued case, it's not so clear what type of object should we study. Should we study a set-valued BSDE or a differential inclusion, like point inside a set, or set equals a set? So that's the equation. So inclusion versus equation. That was, there is some sort of trade-off between studying the two. Also, that's what we have seen in the discrete time analogs. There are a couple of works by this Polish group of researchers, mainly on set-valued stochastic analysis. For instance, Kisielewicz has some works on backward stochastic differential inclusions on a limited class of inclusions. Also, there are works in the forward situation, stochastic differential inclusions and forward set-valued stochastic differential equations. But the backward case for backward SDEs it seems to be not studied because of some reasons, because of some good reasons, because there are some obstacles in studying this kind of an equation. And we will try to establish a simple BSDE, set-valued BSDE, for which we can prove existence and uniqueness of solutions, or well-posedness. What we will do in order to establish well-posedness, what we will do is to prove some martingale representation theorem first for set-valued martingales. There is also some literature on this, so I will also talk about the literature on set-valued martingales. There are already some results, but they are just not ready for our use. So that's why we had to extend the theory for our needs. Okay. Although I should say at this moment that this construction that we propose is not as okay. The construction that we propose is not as general as we want, because for risk measures, we always deal with unbounded sets. Whereas in our framework that I'm going to present today, we will work with the compact valued. Always we will deal with compact valued multifunctional set valued functions. So one needs to extend the theory in several directions. One of those directions is to move from the bounded case to the unbounded case. So in the rest of my talk, so this was all the motivation, why we do this and that. This was all the motivation. In the rest of the talk, I'd like to give some brief overview of the elements of set value stochastic analysis, Because if I just present the BSDE without explaining the meaning of every single term, then this is just some pure formality with no particular meaning. So we really need to follow this program of defining some basic elements, and some obstacles will also show up as we see why this is not a very straightforward extension from what is already done in the literature. Okay. Any questions so far? So let's follow our program. So this was the BSD that I showed you before. Let's first look at it and see if we can make sense out of it without doing anything. Okay. So I would like to see this as a set-valued equation. So what I mean by this is that my terminal condition will be now a random set, a measurable multifunction. The driver will be a set-valued function. Of course, once I have something set-valued on the right, I should have something set-valued on the left. The solution will be set-valued. It will be a set-valued process. This means the input of my driver is also set-valued. And so far, I have no idea about this part. This part is a bit tricky, but let's hope that Z will be a set-valued process too. And we'll see later that this won't be the case. Also, another point is that we have a minus sign here. Can we make sense of it? Set plus set should be understood in the pointwise way, right? Minkowski sum. Set minus set, should we also understand this as element-wise Minkowski difference, or should we do it in a different? Also, I need to explain the meaning of integrals, especially this one, because apparently we know for sure that this would be something set value. So how do I integrate set value functions? In case this is set value process, how do I take the stochastic of the set value process? All of these should be studied carefully before we can even talk about this equation as a BSD. Okay, so here's some abstract framework which we can establish the ground. Let's say we have some nice topological vector space X, okay? Most of the time it will be just RD or some LP space of random vectors. We need to keep track of some important notation. For instance, Kx is one of them. This is my hyperspace of sets, convex and compact subsets of X. Sometimes when X is LP, compact is just too much, and we might need to do weakly compact. So in that case, I will put a little W here to indicate that this is weakly compact. Before thinking about anything topological like limits and so on, let's start with the very basic things. How do we add sets? We do it in a simple way, Minkowski way. But when we do it, the space, this hyperspace with Minkowski addition is not a vector space. For instance, when you do set minus set, A minus A, this is not the origin. This is not a fixed set. You might end up with a very large set, which doesn't look like the difference between two sets. Nevertheless, the addition has cancellation law when you work with compact sets. When you work with unbounded sets, this doesn't work. So if you have A plus C equals B plus C, you can cancel out C, as long as C is convex and compact. This is the cancellation law. It's an important thing if you are going to solve some equation at some point, right? But if you work with unbounded sets like this, try it, it doesn't work. Okay, so when you try to do some basic mathematics with sets, even this kind of thing fails. So there is lack of vector space structure.
For the cancellation, so the condition is only on C. A and B are arbitrary.
Yes, I think C, as long as C is compact, it should be doable. And there is one notion of difference introduced by Fukuhara. So if you have A equal B plus C, you can say that C is the Fukuhara difference of A and B. Of course, this is well defined only when you have such a condition for some C. If such C does not exist, then Fukuhara difference does not exist. You can characterize when this kind of set difference exists. And indeed, when it exists, it coincides with another notion of set difference called inf-residuation. So A minus B in this case is defined as a set of elements with which you shift the B, the second set, and then it becomes a subset of A. So you just try to move your second set so that it lies inside A, the first set. This Fukuhara difference, as long as it exists, it has some nice properties. You can do some little arithmetic with them. The problem is that you need this kind of thing. Even compact doesn't solve the issue. Even with compact set, it doesn't always exist.
For the uniqueness of even A and B.
If it exists,
Each is unique.
yeah, when you work with compact sets, I think it should be unique.
So for the uniqueness, you require compact.
Yes, right. Yes. We are always in the compact space, compact hyperspace. And if we have subsets of RD, we can define Hausdorff distance between sets. This is quite well known. So you look at the axis of sets with respect to each other. This is not symmetric, so you do both, and you take the max so that it becomes symmetric. With this structure, with this distance, it's a complete metric space. So you can now try to take some limits. You can if you want to show that something is convergent, it's enough to show that it's Cauchy, for instance, right? Something to keep in mind, because if you want to solve a differential equation, at some point you need to construct a solution, and it should be done by a sequence, Cauchy sequence, right? So this is something nice to keep in mind. If you try to enforce this to become a norm, like you just take the Hausdorff distance between the set and the origin, it's almost a norm, but because you're not in a vector space, you cannot call it a norm. It's a norm in quotation. And when the Fukuhara difference exists, one last thing about this Fukuhara is that if it exists, the norm of the Fukuhara is just the Hausdorff distance between A and B. So that's something nice about Fukuhara distance difference. So, okay, so this is basic arithmetic. Now we can introduce measurability. What is the measurability of a set value function? So I have a C, which is from omega into K, the compact convex subsets of RD. I call it measurable, or I call it a random set, or I call it a measurable multifunction. If it has some measurability property, it has measurability of pre-images. Pre-images is understood in this sense. You take intersection with a measurable set or a compact set, and then it should be non-empty. So the set of all omegas satisfying this is the measurability for multifunctions. And once you have such a multifunction, you might try to relate it to what you already know, which is random vectors. So do I have a random vector, which is always inside my random set? So I have a C of omega, which is a random set here. So can I talk about a random vector, which I already know very well? X, okay, which always takes values inside C of omega. This X is called a measurable selection. So S0 is a set of measurable selections. So I say that X is measurable selection of C. So that's another notation to keep in mind. whenever you have measurable multifunction, it always has a measurable selection. This is a theorem. Without this, of course, you cannot do anything interesting. If you have a measurable selection, which is also integrable, then you call it an integrable selection. So this is SP, just like LP, L0 and LP. So I have S0 and SP of a random set. It's a closed convex subset of a set of space of random vectors. And one nice thing about this SP sets is that we can use them to characterize random sets. For instance, two random sets that are already integrable are equal if and only if they have the same integrable selectors. So you can characterize random sets through subsets of LP, which makes a nice transition to more probabilistic or functional analytic framework. If you have integrable selections, so you have some integrable selector of C, you can look at the expectation of it, vector valued expectation, and collect the set of all expectations. So that is how Oman defined expectations for multifunctions. So if you want to define the expectation of random set, all you should do is to take integrable selectors and collect their expectations. The result might not be closed in general, but in some situations, you can put some conditions on C so that this set is already closed. But in general, just to make sure you have closed expectation, we take the closure of this. What is this condition on C? Nice condition on C. It's called integrable boundedness. So integrable for random sets means that there is an integrable selector. Now, integrably bounded means that the set norm, which is the maximum distance for origin, is integrable. Okay? So that all selectors are integrable, not just one. All selectors are integrable. This is the integrably bounded case where the situation is much nicer, much more tractable. Of course, integrably bounded implies integrable. And in this case, the set of LP selectors is a weakly compact set. So that also gives some more functional analytic structure on the LP side. You start with your C, and you assume that its set norm is integrable. Then all the measurable selectors are integrable, and they form a weakly compact set, convex weakly compact set. So that's why we deal with so SP of C, which is a subset of LP of RD. So when you treat this as your X, okay, so now you have a convex weakly compact subset of it, as long as this is integrably bounded. And in this case, your expectation is already closed. You don't need the closure. So I create a new space out of those integrably bounded random sets. I call it script LP. Don't confuse it with the usual script LP used in probability. This is just a set of random sets, okay, integrably bounded random sets. I can equip them with a metric, just the LP metric together with the Hausdorff distance. And this is a complete metric space. With this metric, it's complete. Again, something nice to keep in mind in order to take limits. If you have two integrably bounded random sets, you take their Minkowski addition. The selectors of the Minkowski addition is the Minkowski addition of selectors. That's a nice and simple result. Of course, with this result, you can immediately show that if the Fukuhara difference exists, then the selectors of the Fukuhara difference is the Fukuhara difference of selectors. So a result in stated in terms of the Hooke-Vara difference. So we always, in set value analysis, it's very much, we are always interested in making transition between random sets and the set of random variables, set of random vectors. Here is the main tool to make this transition. So you start with a random set. It has measurable selectors, integrable selectors, and so on. So this gives you a subset of LP. If you start with a subset of LP, how can you ensure that it is the measurable selectors of some random set? For this, you need to assume the so-called decomposability property on the LP space. So if you have a set M, which is a set of random vectors, we say that this is decomposable. So if this condition holds, you pick two elements, you paste them together on an event and the complement. The result should still be in M. So that's a property similar to convexity or so you take some sort of combination, you can call it decomposable combination. The result should lie in the same set. So it's closed under taking those kinds of combinations. If you have a closed and a decomposable subset of LP, then there is always a random set, which is almost surely unique, whose selectors gives us M. So if M is closed and decomposable, you can always find an almost surely unique random set C, whose selectors is equal to M. That's a very important tool. Whenever we would like to pass from LP to random sets, we always need this kind of result. If you assume that M is also convex, then your random set is convex. If you assume that M is weakly compact, then your random set is even integrably bounded. If you start with a set which is not decomposable from the beginning, you can always take a decomposable hull of it, which is the smallest decomposable set covering it. So that's the decomposable hull. Basically, just a collection of all decomposable combinations, finite decomposable combinations. You paste them on a partition. The resulting set might not be closed, so you just take the deck bar, which is the closure. If you start with a convex M, the decomposable hull will be convex, and so on. And then the corresponding C, if you start with the weakly compact M, the corresponding C will be integrably bounded. Conditioning can also be done in a very easy way. Just like how we did unconditional expectation, we can take conditional expectation. So just take the selectors, integrable selectors, and take their conditional expectations. The result is decomposable. This set will be decomposable, but not necessarily closed. So you take the closure, you have a closed decomposable subset of L1. So there is a corresponding random set, which we call the conditional expectation of C, given G. So G is a sub-sigma algebra. You don't need to take the deck, because the set, the collection of conditional expectations is already decomposable. If you start with an integrably bounded random set, this set is already closed, so you don't even need the closure. So that's the nice special case. You can also do this simple arithmetic with the conditional expectation, such as this one. Just like how you add integrable selectors, you can add and subtract conditional expectations. Any questions so far? Questions so far? You can interrupt at any time, of course. So now we can move forward to processes, set-valued processes. So I have my usual processes, phi t, which are progressively measurable and square integrable. And now I can talk about set-valued processes, which means at each time we have a random set or set-valued random variable. I won't go into details of how we define things like adaptiveness and progressive measurability for set-valued processes. This is not a very difficult task, but let's assume that we have those concepts, adapted processes, for instance, adapted set-valued processes. In this case, we are interested in looking at adapted selectors, selectors being processes now, not just random vectors. So when you see this filtration in the subscript here, it means that we are interested in processes. So these are measurable selectors, which are processes of a set value. And these are just the square integrable ones in this sense. Now, if I have a set valued process, which is square integrable, I will denote this by script L because it's sort of bounded in this space. So I use the script letter L, just like how I did integrable boundedness for a single random set. And I can just use the same type of metric to study convergence because it's a complete metric space. The set of square integrably bounded set value processes under this metric is again a complete metric space. So one message so far is that we don't have a vector space structure, but we always have some sort of a metric. And as long as we can prove completeness, we can study some equations, hopefully, in this work. Okay, so once we have stochastic processes in the set valued setting, we try to take their integrals. If I have a single stochastic process, a single value stochastic process, these are my usual integrals with respect to time variable and with respect to a Brownian motion. This is just the Ito integral. Now we will make sense of the integrals of set valued process. Of course, the idea is always the same. Just we think in terms of how Oman thought of integrals. We take selectors, take their integrals, and collect them. Hopefully this makes sense. When you take all square integrable selectors of the process, okay, this set, and take the image of this J, in general, this won't be decomposable. Indeed, it's decomposable if and only the set is a singleton. So it's a negative result. So now that's time to take a deck bar whenever we start with a subset of LP, like this, which is not decomposable. So we take the deck bar of it in order to make sure that this comes from a random scheme, which we will denote as the stochastic integral or time integral of the set valued process. So once I take the deck bar, I can say that there exists a random set. I can symbolically denote it by 0 to capital T, pi t dt, whose selectors, L2 selectors is this set. I use this main theorem about decomposability. And this is how we define the integral of a set valued process. We can do the same for the stochastic integral, the dt integral. Just take the image, take the deck bar, and then there's a corresponding set value. There's a corresponding random set, which we can call the stochastic integral of the set valued process. If you want to define the integral from 0 to little t or t to capital T, that's doable. So you just play with indicator functions as you can also do in vector valued setting. What you can also do is to take integrals of not just set valued processes like this, but also set of processes which are not necessarily coming from set valued processes. I give you 5 stochastic processes, which are integrable, sufficiently integrable. You take their stochastic integrals. Now you get a set in LP. You can always take the back bar of it, and there's a corresponding stochastic integral. So this is my so-called generalized stochastic integral. Generalized in the sense that my integral is now a set of processes, but not measurable, not a random, not a set valued process. And you can, for instance, show that you can do addition, for instance. You can do addition. But of course, I need to explain. I owe you one explanation. Why do I need the integral of z? Why is the integrals of set-valued processes not rich enough for my needs? So why do I need this abstract integration for a given set of processes? So this is the question I'd like to explain. And that is very much related to set-valued martingales, which is one of the main tools if you want to study some BSD. It's very easy to define a set-valued martingale because you have a notion of conditional expectation. So it's just the martingale property that we all know, just with a new meaning attached to it in the set-valued frame. Let's assume that the initial value of the martingale is a singleton. Let's say just 0 without loss of generality. Okay, this is an assumption just for now. What we can do is to look at selectors of this process, the martingale, selectors that are already martingales. So these are my martingale selectors, MS. Of course, each martingale, being a vector-valued martingale in Brownian setting, has an integral representation by the classical martingale representation. I can always represent each of them as a stochastic integral. Let me collect the representatives of all those martingales. So this is one representer. I collect all of them. Now, this is a set of processes, but it's not necessarily decomposable. If you want to make sense of, if you want to provide a martingale representation theorem for a set-valued martingale, the most natural candidate for the integrand is this, the set of representatives of martingale selectors. But the set of representatives of martingale selectors is not decomposable. So that's why we introduced this abstract concept of integration. Even if this doesn't make sense as a set-valued process, you can always integrate it because you have this tool, back bar tool. And now Kişielewicz was able to show that whenever you have a set-valued martingale whose initial value is a singleton, you can always represent it as a stochastic integral. Sounds very nice because we have a martingale representation theorem. So if you have some terminal value, let's say you are trying to prove the well-posedness of some BSDE, you are in the middle of it, at some point you need to use martingale representation theorem. So you take a terminal value, you study this martingale, you want to represent it as a conditional, as a stochastic integral. So we want to use the theorem of Kişielewicz. Can we do it? Well, we have to verify this assumption. M0 must be 0. Does this hold? Bad news is that it does not hold unless we are in a very trivial situation. So the only case where for a set-valued martingale M0 is just the singleton is essentially the case where it's a vector-valued martingale, ordinary vector-valued martingale, plus a fixed set. So the set-valued part is not really interesting. Just there is a vector-valued randomness, okay, moving, but you just translate it by a fixed set at time 0. So that is not essentially set-valued. It's just reducing down to the vector-value case, which is not so interesting. So this martingale representation theorem that I showed you is not really applicable for any setting where you have genuinely set-valued randomness. So what do we do when M0 is not a singleton? The problem is that we need to keep track of the initial value of every martingale selector. So whenever you have a martingale selector, okay, there is the representer, but there is also the initial value. So you have to keep track of both, and together they have to be paired. Now I take all martingale selectors, but I look at their representers together with their initial values. Now this is my integrand. This is my integrand, and I can take the image of this integrand, which is not necessarily decomposable. So I take the deck bar, and now there's a stochastic integral. So we change the definition of stochastic integral so that it works, in the sense that we can now prove a martingale representation theorem. So this is the new martingale representation theorem. I change the definition of integral. I have a new concept of integral, which is now a set of pairs. We can find a set of pairs whose stochastic integral is our martingale. You have a question?
I'm just a little curious about this notation, zero minus.
Ah, okay.
Because when we talk about Brownian motion, it's continuous, so there's no.
Zero minus. Why do we choose? Very good point, by the way. The zero minus is there to emphasize that we take care of the initial value.
Yeah, but that if you later on T to T plus, you also have.
So when T equals to 0, it's not 0.
It's actually something cumulative, not just, it's not an increment. So this is a very fundamental issue about stochastic integral. We have to define it in a cumulative way, not like as an increment.
Not just to avoid.
It's a kind of a jump, yes, because you can say M0 minus here, M0 minus here.
Yes,
For
yes,
lack of better notation,
yes, yes.
just so that you don't just automatically assume T equals to 0. So, the problem is that.
So just when we look at it, like in the V process, you have the 0 minus. Brownian motion is continuous, so then.
Yeah.
So we
I know the mathematics.
You can see the record.
Yes, yes, yes. Just to emphasize that we take care of the initial point. Okay, so that is enough preparation. Before the end of the talk, I should get back to BSD. Now this is the simplest form of the set-valued BSD. Set-valued terminal condition, which is square integrally bounded. Set-valued driver, whose input is also set-valued, output is set-valued. The rest is as usual. With one important thing, I don't have dependence on Z. As I try to convince you, Z is a difficult object. So in this work, we excluded the Z part, the Z dependence. It's complicated because it's not really measurable. It's not a set-valued process. It's not a simple task to just look at the time t value. It's a bunch of processes. Even more, you have the initial values and so on. But in this form, I don't see any stochastic integral. It's the simplest form of it. I express this in terms of conditional expectation. So that's a convenient enough form that I can prove that this has a solution, unique solution. Of course, under some assumptions on F, which is the standard assumption, the extension of the standard assumptions in BSDE theory, like the Lipschitz assumption. This time I use Hausdorff for metric, and this is the assumption, and there is some measurability and integrability assumption. Minimal but standard assumptions on the driver. How do we prove that a solution exists? We create a Picard iteration, a standard Picard iteration from the set value framework. Start with 0, and then just run this recursion. Take the previous solution, the candidate solution, and just calculate the right-hand side of the BSD under that candidate solution. So you iterate this way. First of all, you can do it at each t, but we are in the set valued framework. We have to make sure that this is jointly measurable, not just in omega, but also in t, omega t measurable. So is this an adapted process, for instance? For this, we need to handle use a technical tool. So if you have a terminal condition and you look at the conditional expectation martingale of it, we can prove that this set valued martingale has an optional modification. So I don't assume any path regularity, but I can prove the joint measurability.
So again, set is not continuous.
Except under very restrictive assumption in the literature. So far, we don't have a result saying that stochastic integral or the set valued martingales have CAD-like modifications or whatever. We don't have this kind of a result. So my martingale definition was just the martingale property, nothing else. No, I don't say that the CAD-like martingale or whatever. But at least we can say that there is measurability. So we can still continue.
Talk about stopping times.
Yes, we can. This is indeed what it does. We can talk about stopping times. There is an optional projection theorem for set valued processes from 20 years ago. So we used that result from set valued analysis. And thanks to that, we are able to prove that our Picard iteration makes sense. It has progressively measurable modification. That's all we need. We don't have path regularity, but we have progressive measurability. Then to show that the Picard iteration is a Cauchy sequence, you need to prove some estimate like this. So it shrinks over time, over the iteration number. And then with this crucial lemma, it follows that the BSD has a solution, which is unique up to modifications. Because we don't have path regularity, I cannot say up to indistinguishability. I can only say up to modifications. The tools that we used to prove this lemma, for instance, was one, we have this contraction property for set value conditional expectations. And two, we have also some estimate on set value integrals of processes with respect to the time. So these are two properties which are well known in standard, the vector valued case, but when you have the Hausdorff metric, this requires some long proof. I won't go into the sketch of the proof. Let me skip those. So I showed you the simplest form, but indeed we can also work with the different forms of the BSD. For instance, you can get rid of the conditional expectation, but put the set value marking M capital P, M little p. Or you can put the M capital P to the right, so you have some smaller difference. So this is some alternative form of the second form of BSD. In this case, your solution has a Y part and a set valued M part, which is a set valued martingale. Again, as a corollary to the main result, we can prove that this has a unique solution. And finally, with the stochastic integral theory, we can make those terms explicit, 0 to P, 0 to capital P. So we can show that there is a solution with a Y part and then R. So we just make those martingale terms as stochastic integrals. So that is the third form I'd like to show you. And these are the results, the main results that we have. This can be extended in many ways, as I tried to explain also at the beginning. For instance, how can we add the dependence on the R part in the driver function, which is essential for risk measure applications? How can we remove boundedness? And can we connect this BSDE to BSDIs, the inclusion counterparts? These are related to the BSDE stuff. They are not easy extensions, but we have some ideas. Also on the martingale part, there are some open problems. In general, when you deal with a set value stochastic integral of this form, this is only a sub-martingale, but not necessarily a martingale. What I showed you was a result which says that if you start with a set value martingale, then it has a stochastic integral representation. But when you start with a stochastic integral, is it always a martingale? The answer is no. We are indeed characterizing this behavior, the martingale property, currently. Path regularity, as it was already raised during the talk, we don't have path regularity of stochastic integrals. This is one of the challenging tasks to do. And also, this stochastic integral, let's go back to the case where the initial value is 0. You don't have time additivity of stochastic integrals, which is very unsatisfactory. Can we come up with a better definition of stochastic integral where you have this kind of additivity and form additivity?
For the solution Y, do you have the time consistency?
Solution Y.
Y P equals the conditional expectation of YS plus the universal of P.
That should be okay. This part is fine. Yeah.
That's only for this because the form. Actually, in the inclusion case, it's also in the.
It's in the conditional expectation form. Yes, it's the inclusion.
For that to be true, we need to apply some conditions on F.
How about the figure?
I mean, so the last plot is you replace it with P instead of B.
That works. That holds.
That's always.
That's true.
Okay.
Yeah, I think in all the, at least in the compact case, it's true. It's the situation, the difficulties always, I mean, most of the time they come from the stochastic integral, not the DT integral. Okay, that's all I'd like to say. Thank you very much.